Hi guys, Kenna here. So today we're going to be continuing our look at energy use and starting to take a look at fossil fuels, which is the main focus for this particular unit, fossil fuels and non-renewable energy sources. Today we're going to be looking at the world energy use and the laws of thermodynamics. Let's go ahead and jump right in. Here are essential questions for today. Number one, what is energy and why does that matter in our modern world? Number two, what are the laws of thermodynamics and how do they relate to our use of energy? Number three, how is global energy use divided and how does this compare to the US? Number four, what does the future of energy look like? And number five, will fossil fuels run out? So let's start with that first question. What is energy? So, at its simplest level, energy is the ability to do work. And this comes from physics, which is another class that I teach. And so, when we start looking at work, it has a very specific scientific definition, which I'm not going to go into in great detail here. But um, work, we use energy to do work. And the combination of all energy and matter make up the universe. Matter is substance, and energy is the mover or actor of substances. So energy causes change. There are two primary forms of energy that we talk about in physics. Those are potential and kinetic, and they are related to each other in terms of being able to convert it from one to the other. Similarly, Einstein's E equals mc squared relates energy and matter to each other. Okay. Now, why does that matter in terms of environmental science? Well, in environmental science, we are taking potential energy or stored energy and we are using it, which is kinetic. And this relates in terms of thermodynamics. Thermodynamics is a branch of physics concerned with heat and temperature and their relationship to energy and work. In particular, it describes how thermal energy is converted to and from other forms of energy and how that affects matter. Now, we utilize a lot of energy in just about everything that we do. And as we do that, some of that energy is converted or lost, we typically say, in the form of heat. Now, thermal energy is the energy of a substance or system due to its temperature. The energy moving or vibrating molecules is what we're mostly kind of focusing on. So, thermodynamics involves measuring this energy, which can be exceedingly complicated. But let's try and simplify this down into some basic rules. These are the laws of thermodynamics that come from physics. Now, there are three principal laws of thermodynamics, and each law leads to the definition of thermodynamic properties, which helps us to better understand and predict the operation of a physical system. Remember our example of system versus surroundings? That's going to come into play here. So, the first law of thermodynamics states energy can be changed from one form to another, but it cannot be created or destroyed. So this is law of energy conservation. The total amount of energy in the universe, and matter for that matter, remains constant, merely changing from one form to another. Second law of thermodynamics. The disorder of a system, an isolated system, not in equilibrium, will tend to increase over time, approaching a maximum value at equilibrium. Now, we talk about this a lot in astronomy or astrophysics. When we start looking at the potential ends of the universe, we talk about the big chill, the big crunch, the big rip. If you have questions about these, please feel free to reach out and we can talk about how this relates to the second law of thermodynamics. And then we have the third law of thermodynamics, which states that as temperature approaches absolute zero, the entropy of a system approaches a constant minimum. This is equilibrium. This is uniformity. Okay. So, what we're really looking at is kind of focusing on first and second law for what we're doing here in environmental science. So, the first law, in terms of practical use, according to this law, during energy conversions, no energy is created or destroyed. Again, it's simply changing form. And then, in terms of use, the second law, when energy changes from one form to another, it always goes from a more useful to a less useful form. So there's lost energy. It's not that it's actually lost, but it's converted into a form that we can't directly use. So you want to use energy more directly to its original source, if at all possible. Okay. So how does this relate economies to the environment? Sufficient and secure energy is the main enabler for welfare and economic development of a society. As energy related activities have significant environmental impacts, we'll review those in a little bit. It is necessary to provide an energy system which covers the needs of the economies and preserves the environment. And this is going to be a constant theme as we go through the rest of this term. Okay. We need to have affordable, available energy, and we need to protect and preserve the environment. So, the future of a sustainable planet is going to rely on diverse technologies. With the diversification of technologies and resources in the energy sector, there are many opportunities. The enlarged complexity also leads to increased challenges in terms of making and maintaining a single unified grid to provide electricity to everyone. With increasing volatility in the markets and declining resource availability, it's necessary for stakeholders to employ strategic decision making, and this need is becoming even more and more important than ever before in the past. Again, remember our key focus. We need available, affordable electricity, energy, right? But in a way that protects and preserves the environment. So, when we go ahead and take a look at 2014 data, and I'm going to ask you as part of your activities today to look at more recent data, we see a breakdown of renewable versus non renewable. And on a global scale, we're pretty comparable 10% renewable to about 90% non renewable. But if you're thinking about this in terms of sustainability, hopefully you recognize that non renewable resources are not long term sustainable. Historically, they've been cheaper and easier to access and transport, which has made them very appealing as an energy source. Okay. Now, this is something that's going to have to be examined moving forward. Some of these, especially oil, natural gas, and coal, are more polluting. But that doesn't mean that our renewable resources don't have some environmental impact. But we have to think about trade offs and what our risks are for our planet. And a lot of the focus right now is on greenhouse gases, and in particular, CO2. Here are some more recent numbers from 2017. This is US energy consumption. Again, looking at total BTUs, I guess that's British thermal units. We could look at the BTUs. Probably the more scientific unit would be to use a joule, but a heavy chunk of that is going to be petroleum. You'll notice that from the previous numbers we showed you, the renewable energy makeup is increasing by about 1%. And you're seeing a decline in coal because this tends to be one of the most polluting forms of energy that we have. Okay. So as you start to look at these numbers, and I'm going to have you look at them a little bit later today as part of your assignment, I want you to really think about how diversification of this model could benefit us and how we can ease the transition into more renewable resources by using the non renewable resources more efficiently and more effectively and not wasting energy. And that's going to end up playing a big role here too, is trying to optimize our energy use so that we're using what we need, not using what we don't, not wasting any of it. So, for the past 15 years, we've seen unprecedented changes in the consumption of energy resources. Unexpectedly high growth in renewable market, in terms of investment at least, new capacity for high growth rates in developing countries have changed the landscape of the energy sector. We have seen the growth of unconventional resources and improvements in technology evolution for all of the forms of energy resources. So, we've been able to go ahead and make non renewables cleaner, and we've been able to make renewable energy more efficient. Although we'll talk a lot more about this throughout the course of this term, and we'll start look at the cost benefit analysis of what energy forms we utilize. And this has contributed to falling prices and the increased decoupling of economic growth and greenhouse gas emissions. And we'll talk about that as we go ahead and go through this unit, as we start looking at not just the types of energy, but we'll look at the impact in terms of the climate and in particular the atmosphere and things like air pollution, acid rain, etc. Now, most countries have achieved a more diversified energy mix with a growth in community ownerships and the evolution of what are called microgrids. These are smaller um, grids that don't tie into everything. And by doing that, you are relying on your microgrid, but at the same time, you're able to kind of detach yourself from the bigger fossil fuel driven energy production systems. So I know we've gone over this last term and I'm going over it here again, but I think this is an important concept to make sure that you understand this system versus surroundings relationship. An isolated system does not exchange energy or matter with its surroundings. Does not. This is a closed system. In fact, there are a few, if any, systems that exist in this world, however, that are completely isolated systems. So, for purpose of resource use on our planet, nothing is isolated, and every decision impacts every other decision. So, I want to go ahead and, as we start to close out today, get you really thinking about, will fossil fuels ever run out? It's a big thing that goes around on the internet, Facebook, every so often. Um, but will they? And if so, what timeline are we kind of
We've
looking
all
at?
heard that fossil fuels won't last forever, but why? And if they are set to run out, how much is left and when will that happen? To dig to the bottom of this one, we first need a quick refresher on how fossil fuels are created. And sadly, no, they're not mostly dead dinosaurs. You see, the vast majority of our fossil fuels come from the remains of plants and animals that lived around 300 to 400 million years ago. And we don't see the first dinosaurs until around about 230 million years ago. So, when these plants and animals died, that very, very long time ago, they were covered in layers of earth or silt. And because of the combined actions of three things: one, the compression from the weight of all that stuff; two, the microorganisms in there decomposing the content; and three, the heat underground, that transformed them into potential fuels. Coal is the remnant of ancient plants, whilst oil and natural gas mostly come from marine creatures, with natural gas being made in deeper, hotter regions where the oil gets a little bit more cooked. Now, we dig or drill this stuff out of the ground, and because it has been accumulating for a long time, initially there was a lot. But because it takes so long to make, we're using it much, much faster than it can possibly be replaced. This means that there is effectively a fixed amount of fuel on Earth, and we're using it up. So, yes, fossil fuels are going to run out, but what is left, and when will that happen? Well, we can fairly easily tally up what's known as our proven resources, the supplies that we know the locations of and we think we have a good chance of getting to. In their statistical review of world energy, BP estimated that the world had just over 1,700 billion proven barrels of oil in 2014. That's enough to meet 52.5 years of global production. They also estimated just over 187 trillion cubic meters of natural gas. That's enough for 54 years. And 891,531 million tons of coal, enough for a whopping 110 years of global production. But there's also the stuff that we know about, can't reach, but think we might be able to get to someday. Hard figures on that are, understandably, tougher to come by. But oil and gas consulting firm Rystad Energy estimates total probable global oil reserves at 2,092 billion barrels, which is enough for about 70 years if our use doesn't go up. The total fuel resource, the amount of fossil fuels that could be out there that we know nothing about, could of course be even higher. But around 4 years ago, an idea came out that there actually is plenty of oil left, just that we haven't got around to getting it out of the ground yet. This means the numbers for the potential oil out there could in fact be way higher. We've already seen humanity use new technologies to access and use fuels that we couldn't get to before. Things like new techniques to extract oil where it's all mixed up in fine-grained sedimentary rocks, like shale, or using high-pressure fracking to extract more oil and gas from the ground. One thing stopping us using these new technologies to extract fuels is that the rising energy costs of extracting it could be just as damaging as the oil running out. Despite the cost of oil, the amount being extracted has actually remained constant, about 75 million barrels per day since 2005. And this means a plateau has been reached, where supply cannot match demand. It's also worth pointing out that fracking is far from ideal. It's been claimed that it has been linked to earthquakes and toxic tap water. We've already seen how the economics of getting to the fuel can outweigh humanity's demand for it. In 2016, around 460,000 barrels a day of high-cost production like fracking was shut down in the US due to the cost. But that just means surely it's there for later, when the economics are right? Well, maybe we need to leave it there. The planet is warming due to the burning of those fossil fuels. Burning fossil fuels releases carbon dioxide into the atmosphere, traps heat, and it causes a greenhouse effect. It's been estimated that we cannot burn more than about a third of those proven resources if we have any hope at all of meeting plans to keep the temperature rise at 2 degrees centigrade or less. Although it may feel that we don't seem to be in a particular hurry to look for alternatives, energy transitions have always taken a long time. It took over 50 years for coal to replace wood as the world's leading source of energy, and another 50 years for oil to overtake coal. So, here's a promising thought. In the end, with so many options for renewable sources of sustainable power being developed, we might actually never have to answer this question of what happens when the oil is finally all gone. Right, this is one where we really want to hear your opinions about this whole subject. Put your thoughts down in the comments below. Subscribe to the channel if you haven't already, and then you'll get to know whenever we release a new one.
So what I want you to be thinking about as you go through this is, yes, we may not actually run out of fossil fuels. Yes, it's a non-renewable resource, but the bigger concern is actually the impact it has from using these fossil fuels on terms of global climate change. Okay, so as we go through this unit, there are four major categories that we're going to look at. In this unit, we're going to focus on oil, nuclear, and natural gas, different ways to extract them, how much, what is the impact. And then later on in this term, we will go ahead and focus more on the different forms of renewable energy. Okay, so oil, nuclear, natural gas in this unit. And then in another unit, we'll go ahead and look at renewable. All right, so that's all I've got for you today. Next class, we'll go ahead and explore oil in some more detail. So stay healthy, stay safe, and I'll talk to you guys soon. Take care of yourselves. Bye-bye.